So we will be continuing today our discussion on operators. And in the last video, I left you with an exercise as to confirm the linearity of the operator as defined like this. This is the complex operator. It's a complex conjugate operator. So this is the operator which accepts a function f and converts it to its complex conjugate. And if you check for the let's take, as we will proceed as we did for the previous case, we start with two functions, complex functions obviously, f and g, and take them and operate the sum of the functions with the a operator. So it's actually f plus g whole star, complex conjugate of f and g, sum of f and g. And we know that if we take complex conjugate of the sum of two complex numbers, it's actually the sum of the individual sum of the two complex conjugates. This should be known from ideas of complex numbers. We can also check by taking two complex numbers and finding out. We know this as an idea. Now what is EF? It's obviously F star, and EG is also obviously G star, plus EF plus EG turns out to be F star plus G star. And we have the simple relation that A acting on F plus G is equal to A plus F E. Both sides of the equation hold true, and both sides of the equation are equal, and thus the first condition will hold true. The second condition, on the other hand, is a little complex. It is a little is the word grasping part, important part. So we have AF. So what if we take a function CF, and this will actually be equal to 1 by C. Actually CF whole star. So this is actually, and we have a product of two complex numbers. This should be actually equal to C star into F star, and if we have C into, if we have this should be C into F star. But are the two sides of the equation equal? They can be equal actually. They can be equal provided C star equal to C. That is, the complex conjugate is equal to the complex number. This is only valid if we take real numbers, right? So the constant C, if C is a real number, then the equation, then both the sides are valid, are equal, and linearity is valid. But what if it is not a complex number? If not, then linearity of operator is invalid. So linearity depends on the constant C. If C is a real number, then the linearity is valid. If C is a complex number, that is C star equal to C, then C star is for a complex number, that is containing both the real part and imaginary part, C star is not equal to C. For number containing both real and imaginary part, linearity is linear. And in this case it is a purely real number, no complex, no imaginary part at all. So for no purely real number, the operator is totally linear. Okay, so we had two conditions for linearity: AF plus G, AF plus G, and then we have second condition also, that A of CF is actually C. If we combine these two conditions, like this, that we have F1, F2, F3, all functions with C1, F1, C2, F2, C3, F3, all functions with C1, C2 dot 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 being constants. Then we have A acting on C1, F1 plus C2, F2 plus dot dot dot, let's say till Cn, Fn. What should this be equal to? Obviously these are all functions, so by the first property we can actually, by the first property of linearity, we can write this as A C1 F1 plus A C2 F2 plus dot 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 plus A Cn. Now by the second property, the constants come out of the operators, and C F2 plus dot 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 plus Cn A Fn. Since A is a with A being linear. Okay, so we have taken the consideration that A is linear, and thus we have this. That is, we started with this and we end up with this. So what have we done is, we have taken a, this is called a operating on a linear combination of functions. We have operated the linear operator A on a linear combinations of functions f1, f2, f3, f4 until f, and thus the operator A, by notation, this is actually nothing but sigma, there is a summation on Ci, Fi, I will be going from 1 till n, and this A is acting on this linear combination of functions, which is also a function. Okay, and this actually came out to be very beautifully, that this operator A has moved inside as if, and this came out to be Ci A Fi I equal to 1 till n. So this is the linearity, combined linearity condition. And if we have if the operator happens to be linear, this is the combined condition for linearity. Okay, so our discussion on linearity ends here. although we can go on and keep taking examples, but this is where I think it is more than sufficient to move on to the next topic. To move on to the next topic, we must talk about something called as eigenvalue equations. So eigenvalue equations are equations which involve operators, right? Which involve operators. So we have an operator A which acted on some function f of x, right? So this is our input function. If at all the output of this equation, operator acting on f of x, is actually the same function f of x multiplied by some constant a, this is the output function, then this is actually referred to as, these type of equation in maths are referred to as eigenvalue equations. And why are they called eigenvalue equations? Because these equations give the same function, operate on the because the operator has operated on the function to give us the same function multiplied with some constant a, and only thing that has changed is actually this a. Changed in the output is this a. So this a is actually referred to as the eigenvalue, and this f is referred to as the eigenfunction. And this is the only thing that we need to know here. And the thing that we must know is actually the definition of we must be able to identify which is the eigenfunction, which is the eigenvalue. Okay. And we will start straight away with an example. If the operator a b d dx, the derivative operator, what is the corresponding eigenfunction? If the operator is the double derivative operator, again what is the eigenfunction? For the ddx operator, what we are basically asking is this ddx operator will act on some function f of x, will give a, will give some constant a, which is actually the eigenvalue multiplied by f of x, right? This is our idea. And if you notice, this is actually a differential equation with a known solution. So this f of x, the eigenfunction, will be something like e to the power ax, right? And you can check it out that the derivative of dx f of x is a e to the power ax, and this is a, and e to the power ax can be written as f of x. So this is an eigenvalue equation. What about a double derivative operator? A double derivative operator will act on f of x to give some a to f of x, right? And this is actually, and you can notice that this f of x is actually some sine root ax or cos root ax. In fact, e to the power root ax will also work here. If you check, some e to the power kx should also work, not root x. So let's call e to the power kx should also work here. Right? We can check it out very simply, that if we take sine f of x equal to sine root ax, we have dfx upon dfx ddx on fx. We have root a cos root ax, and again the derivative should yield us that a sine root ax with a negative sign. So indeed so what we should have started with should have been a minus sign, and this is a constant, so it doesn't really matter, and the sign can be different. The sign is not an issue for eigenvalue equations. So if you have an equation with eigenvalue a, so eigenvalue minus a is also accepted. The sign reversal is not an issue for an eigenvalue equation. Okay, and so these are some piece of information. Let's go straight back to some problem. And first problem I would like to bring your mind to is the very fundamental property of operator algebra, that if you have a sum of operators, I hope I have been able to make it clear that if you have a sum of operators acting on f, this is actually equal to af plus bf. This is not confuse it with the linearity property, but this is an operator which will also hold here. So let's say, using the same example, that we have a as the famous double derivative operator, and b as some multiplier operator x. So what I would be asking is e to the power ax square an eigenfunction of a plus b. Let's try and figure this out. That d2x dx, that is double derivative, plus x acting on e to the power x square. What is the result? So what we have to do is just find this out, and this is actually your a plus b. fx. In fact, this is also true for a negative sign. Forgot to mention that a plus minus b on f is actually af plus minus bf. So ddx on e to the power ax square, what is this? This is actually 2ax to the power ax square. Again derivative, taking the derivative here, it will be important. So we need the double derivative operator acting on f of x. So this is 2ax multiplied with this is 2ax for the whole square, but it's ax. Okay, and then we have x equal to x e to the power ax square. We have x e to the power ax square, which is actually x e to the power ax square, and add up. So we have d2x dx2 plus x to the power ax square is actually equal to e to the power ax square taken common. We have extremely sorry, I made a mistake, calculation error have d2 dx2 on 2ax e to the power alpha ax square, and this is the error I made. So this is actually 2a. Actually, exponential functions have a very easy way to, we can have a very easy way to compute the derivative. So we have e to the power x squared, so write the exponential part first, okay, and then then apply chain rule. We have this the product rule. So this is the u part. So first derivative, take its derivative, this is actually 2a, and then take this derivative, and this is actually 2ax, right? And this is the answer, 2x. So yeah, this is another 2x, right? This is 2x square, and verify e to the power ax square is actually equal to x e to the power x square. So we have e plus b acting on f. We have e to the power ax square taken common, 2a plus 2ax square plus x e to the power x square. So can you tell me whether this is an eigenvalue? So this is f, so this f is right here. So we have 2a plus 2ax squared plus x. Is this an eigenvalue? So is this an eigenvalue equation? Not at all. So this is not an eigenfunction. Why? Because you see this, have a look at this constant, that is this pre-term of f. This term is not independent of x, that is, it is not a constant. So only in a certain condition only will it be an eigenvalue equation. How do we derive that condition? Actually, we say that this has to be a constant. So we have to, what do we have to do here is this eigenvalue. So this this part is only x dependent, right? So the x dependent part now has to go away from this equation. So thus we have x plus 2ax whole square, this part should equal 0. So this is a condition for eigenvalue. So this equation, for this equation to be an eigenvalue equation, what should be the possible value of a? This is what I am trying to determine. So this is x is equal to 4a square x square plus 2a plus x should be 0. One situation is x equal to 0, which is a trivial solution, because if x equal to 0, then the equation is valid for only one value of x equal to 0. So this is trivial. So the non-trivial part is 4 alpha square. Let's take we have removed x common. So we have 4 alpha square plus 1 into x equal to 0. Or the x part is equal to 0. A. So a came out to be, a square came out to be 1 by 4. Right? Minus 1 by 4. Okay. Thus we have a equal to 1 by So this is an eigenvalue only for one value of I, one value of a, that is f of x equal to e to the power x upon 2i, x square by x e to the power x square, ax square was the function, so x square by 2i, right? So this is a complex value function, for this became an eigenvalue. Okay, so this is the condition for a. Now we can also do another example with d2 dx2 plus ax square acting on e to the power ax. Okay, this can also be done, and we can also derive the condition for k. We can also derive the condition for a here in terms of this k, and this a will actually come out to be I root k upon. You can check this. Now let us discuss an interesting case on the composite operator d dx plus x whole square. If we have such an operator, how do we deal with this operator? Because this operator is actually d dx plus x into d dx plus x, right? So what I am trying to convey to you is actually the algebra of these operators. How does the algebra work? And this operator, and we shall go back to your basic simple algebra of a plus b whole square. We know that this is actually a squared plus 2ab plus b squared. But how do we arrive at this formula? We arrived at this formula by simple expansion, by simple algebraic expansion. That is actually EA, then this was BB, then there was a BB, and then there was a EB, and then there was a BE, right? And then we stated that A was actually AA was A square, BB was B square, AB was, and we stated that since multiplication was a commutative thing, so it doesn't really matter in which order we multiply anything. So AB was equal to BA, and we have AB plus A, and then we have A squared plus B squared plus 2, or rather in the binomial expansion form we have A squared plus AB plus B squared, right? The same thing applies for operators, right? And we shall apply the same thing, but there will be a slight difference in case of operators. So let us copy this thing and paste it right. So first idea is we will have ddx on ddx. This is ddx. So let us make the general operator derivation first. So this is the same as if we have two operators, composite operators, and take this square, it is actually equal to AA plus EB plus AB plus B. Problem is, regarding this part is okay, that the first part we can easily write as a square plus b square plus b square, reminding ourselves that is the square on top of it, the 2 on top of the superscript is actually telling us about that this operator will be acting on the function twice. Okay, but what of this part is that AB and BA are not always commutative. Remember from the first video that I told you about the commutative. So AB and BA were not always found to be equal, right? So AB and BA have to be left on as it is, as we cannot make this assumption that AB and BA were are indeed commutating with each other. So this has to be left as it is, and we cannot unfortunately write this as 2AB or 2BA or something like that. That can only be written if we have two commutative the, the two operators A and B are commutative. And this should actually remind you like something like a matrix multiplication matrix. If we have two matrices A and B and take this sum and take this square root, and take this square, then that is actually A square plus AB plus BA plus B square. The thing is similar, that the matrix multiplication is not commutative. Similarly, the operator multiplication is also not necessarily commutative. Matrix multiplication is also not necessarily commutative. So you can draw that idea from there. Okay, you get me right, that the matrix multiplication, if we have two matrices A and B, then we cannot necessarily say that AB was equal to B. This is not, we cannot say this. So we had that example that we want to talk about, and if we have such an example, we will have x is equal to d2 dx2. First, the derivative operator squared, which would mean that the double derivative operator plus x squared, the scalar operator, scalar multiplier operator squared, and then we have ddx on x operator, and we have x dx. Okay, so these are our operators, and these do not have an individual meaning unless there is a function attached to them. So this is what we have, right? We remember from our first video that the commutator x ddx, what was this? This is actually minus 1, right? So this implies that x ddx minus ddx on x is actually minus 1. Okay, and if we have this, then x ddx was actually equal to, send this to the right hand side, ddx acting on x plus 1 rather than minus 1. So put this back into our original equation. The original equation looks like d2 dx2 plus x squared x ddx is ddx x minus 1. So we have 2 ddx x minus 1. So see how it turned out, that we have the operators. If we call, let's say, ddx as the operator d and x as the operator x squared, x is the operator, okay, so then this turns out to be d squared plus x squared plus 2 dx minus 1 is is actually equal to is actually the result of b plus x whole square, right? So this is how operator algebra turns out. You have to consider and calculate and do everything that you can do mathematically. Every mathematical manipulation is possible, and this is how sometimes things may turn out, right? So this is, I think this should be enough for today, and in the next video maybe we will start off with another important part of operators, which is actually the Hermitian operator. Idea of Hermitian operators we started.